Thank you. I'm going to tell you about this. Before I start, I mean, it's just so great to be here and to see so many friends, and real huge thank you to the organizers, and especially to Alison, who I think it's clear she's put in a huge amount of work to make this happen. I'm going to tell you a bit about the GM Galaxies program, which is what I've been busy with during the pandemic, I guess. It's a program which you've heard a little bit about. You've already seen our main codes if you came to tutorials earlier in the week. But the basic idea is to try and use simulations, not so much as a way to produce statistical samples of objects in the universe. So obviously, that's a hugely important thing to do, but it's more to kind of pose tightly framed questions and try and answer them about the physics that's going on in galaxy formation, and think of simulations more like a laboratory, in the same way that you might think of a scientist going in and having a hypothesis that they're going to test with an experiment. So this is something that's been kind of developing slowly over many years now, and a huge number of people have been involved in various ways over the years. I'm going to be highlighting some of their work, but I can't possibly highlight what all of these people have done. So I just wanted to say up front, a big thank you to all the collaborators, some of whom are here, who have made this possible. And I needed to focus in, I think, on a few results for this talk. So what I thought I would try and give you just a flavor of the stuff we've been doing in three categories. So first of all, I'm going to talk a bit about our thoughts about galaxy quenching and the connection to morphology of galaxies. Then I'm going to say something about dwarf galaxy stellar masses and how they're determined, especially down at the faint end, where, of course, there's a lot of interest from Ferran and others in this room about exactly how that happens. Then I'm hoping there'll just be a couple of minutes for me to tell you something also about some of the machine learning work that we've been doing, which is quite complementary to the more straightforward simulation work. So I'm not going to say too much about the underpinnings of this. I'm going to show you the one slide with the kind of gee whiz mathematics on it. If you were at the workshop, the tutorial earlier in the week, you heard quite a lot more about how this actually works. In brief, what we're trying to do is, instead of just creating one set of initial conditions for a galaxy, for a Zoom galaxy, we are trying to generate multiple sets of initial conditions for a galaxy. So we start with one set of initial conditions, and then by one means or another, we decide, actually, we'd be interested in this galaxy if it did something slightly different. And so by one means or another, we end up with a set of initial conditions which all vary in some systematic way. The actual differences we're talking about here are quite carefully constructed so that they don't mess up lambda CDM or lambda SIDM or whatever the cosmology is that you want to run with. They are tiny and they're smooth and they maintain the power spectrum of the universe. So here is an example from Nina Roth's work, very first paper on this idea back in 2016, where she's making quite a big change to the merger history of a galaxy. But if you look in the initial conditions, so this is the initial conditions, and the sharp bit is the zoom region, and the fuzzy bit is the unzoomed, a portion of the unzoomed box. The differences are really tiny. So I can flash backwards and forwards for you. See, there we are. That's 2 years of code development right there. These changes are, they are really small, and they're intentionally really small because we know that gravitational collapse amplifies quite small differences. When you go forwards in time, those two initial conditions, they generate basically the same cosmic web, same kind of structures. But in this particular case, you'll see, although they're forming from the same filaments, and in fact, object by object, you can find all the same objects, the collapse happens at different times. So right here, where I've paused it in the unmodified case, these two major progenitors here, it's almost a one-to-one merger. They're about to merge. Whereas over here, they're still actually quite some distance apart on that filament. And that's at the same time in these two different simulations. And so then when you go forward in time, things play out slightly differently, but you have the same set of objects involved and the same large-scale structure around them. You just have a different time of collapse, and eventually you get to the same mass of galaxy as well. These are just dark matter halos, in fact. And Nina was particularly looking at the relationship between collapse time and concentration, and you can kind of pull that out by doing these kind of experiments. So, I mean, why is it good to do something like this? There are a number of reasons, but to give you two, I mean, one is that you have infinite tunability. So it's not just that you can make two sets of initial conditions. It's not like you can just contrast these two. You can actually go back and maybe you make a hypothesis based on the two that you originally have, but then you can go back and you can make more. You can do intermediate cases or more extreme cases. And you can see, does our hypothesis for how galaxy formation proceeds, which very often is just done by looking at statistical correlations, does it hold up under this kind of causal test where you can go in and tweak things and see, okay, does this actually follow the hypothesis that we have? And on top of that, you also just don't, I mean, the other way you could do this is by picking out a bunch of objects from a larger volume, which have kind of the properties you're looking for, like maybe you would pick out one that has a major merger and one that doesn't have a major merger. The trouble with that is you would get different environments in each case. You know, you can't go into a box and expect to find two things that are identical except for the one thing that you wanted to change. So you would get a bunch of confusion from that way of doing the experiment. And that's, again, why making these minimal changes is really good, because, I mean, that's an example on the right where at the output redshift, you can actually find the same galaxies sitting in the same configuration, maybe very slight differences in the configuration because gravity is a long-range force and everything gets a bit correlated with everything else. But basically, you know, you can change the history of a galaxy without changing the environment that it's sitting in. So that's why we like to do it. In fact, just recently, we turned this inside out. I'm also quite excited about this. We haven't yet done it on galaxy formation simulations, as well as trying to change the galaxy but leave the environment the same. You can do the opposite and say, we want the same galaxy, but we want to put it in a different environment. This is Corentin Cadieux's work from last year, where if you look at this, these are the initial conditions. What he's done is he's got this. So this is a box, and he's cut out this sphere from the box. It's in the initial conditions. This is just a Gaussian random field in the initial conditions. He's cut that out and pasted it over into the right-hand side. So if you look on the right-hand side, out in the red region, that's a completely different Gaussian random field. In the middle region, it's the same from the left realization to the right realization. You can see like this overdensity, for instance, is also there, but that overdensity, say, isn't there on the outside. So you can cut something, put it in a new environment, and then run that forward in time. All still, by the way, consistent with the whole thing being lambda CDM cosmology. And so, you know, this is a case that he ran just to show that you get the same kind of formation history overall inside, but actually, you know, you start to see what are the long range effects of the environment. You have something very different going on out here compared to in here. And he started measuring, well, how does that affect the formation of, in this case, a cluster here. As you can see that the cluster on the left-hand side has actually already collapsed. The cluster on the right-hand side is still in pieces. And so these kind of long-range effects of environment, I think this is going to get much more exciting when we do it with baryons, which we haven't done yet for this particular case. We're pretty excited about doing that. But anyway, that's the sort of new kid on the block. Mainly what we've been doing is the opposite thing, where you keep the environment fixed, but change the history of the one object. And so that's mainly what I'll talk about. So now I can actually say something about the work on galaxy quenching and morphology. I mean, the first paper we did on this was back in 2017. Now this was with Changa and Stinson and Tremel. And basically, I mean, it's basically Romulus, but in a zoom, and where you have three, or actually we had more than three, but here you see three slightly different versions of the galaxy where we have changed the merger ratio. So where it's paused in the history of the universe, you can see that you've got this same galaxy in the same sort of infalling galaxy in the three cases. Here it's about, if I remember rightly, about a 1 to 3 merger, Whereas over here, you can probably see by eye, that's a much smaller object. It's about 1 to 10. You'll also notice that the merger is going to happen at a slightly different time. When you change the mass of some infalling structure, you do also change how quickly it falls in. So it's not like 100% clean thing. And it couldn't be 100% clean thing, because you've got to maintain all the right long-range correlations to make this an actually cosmological experiment. But it's as close to clean as it can be. These changes, the changes in the timing are quite small. They're a matter of, a couple of 100 mega years over the 14 billion year history. So off it goes. In the enhanced merger case, you can see a ton of feedback being pumped out. It's pretty obvious something bad is going on there. A little bit in the reference case. In the suppressed merger case, it's much less angry. And what you find when you zoom in on the galaxy at the end of this experiment is, in the suppressed merger case, you still have a star-forming galaxy at the end of it. In the enhanced case, you have a very red and dead thing, which is actually quite diffuse from the very big merger that it's experienced, and the reference case is somewhere in between. And just to say that this is totally to do with the interaction between the black holes and the merger history. You can absolutely pinpoint that with this. We switched off black holes and reran them. So I could have told James and Ben that's very expensive, even in a Zoom, that these, like the thing on the right, which is not the real universe at all, takes like 5 times longer to run easily than the thing on the left. Anyway, it carries on forming stars if you do not have the black hole, or if you don't have a sufficiently major merger. So it's quite a nice, clean test in that sense. But people started asking us, well, what about stochasticity? It's all very well running 3 simulations, which are supposed to have controlled changes, but we know that the feedback can be quite stochastic. Ben's work has shown very nicely stochasticity, small stochasticity in feedback can be amplified hugely. And so you might worry, well, actually, you could just be looking at random scatter that you're then interpreting as something significant about the changes in the initial conditions. So John Davies has a nice solution to this. Just rerun the simulation. And because these are zooms, they're relatively cheap. So in his recent work, and I'm afraid this is with the Eagle code, sorry, but it's the same basic theme. He's rerunning these ones 10 times, in fact. Same kind of experiment that I just showed you, some small differences, which I won't bother you with right now. But just to say, so on the left-hand side, he's showing the mass buildup over time. You can see really it's not so much about changing the merger here, it's more about changing the collapse time, because he's got an early forming case, which kind of forms super early and then plateaus in its dynamical mass, and a late forming case where the mass assembles quite recently. And that also leads to big differences in the final galaxy. Even though they've got the same total dark matter dynamical mass at the end, they end up looking very, very different in terms of their star formation rate. But what John's doing here, the bands that you see, they're the uncertainty bands coming from the stochasticity in the feedback and the way that that gets amplified. So just literally rerun the simulation, different random seed, but same initial conditions. And you get these kind of bounds on how uncertain should you consider the specific star formation rate in this case to be. And you can see it nicely. You can continue to separate the effect of history from the effect of stochasticity and feedback and so on. So in this work, what we've been able to do, in fact, is tie it not just to the way that mergers take place, and the mergers kind of enable the AGN to do a lot of damage to the galaxies. It's not so much that the AGN accretes at like Eddington and goes like the old simulations where feedback went a bit crazy. It's a bit more moderate than that. It's more about how the disruption enables the AGN to couple quite efficiently to drive out the ISM, and most crucially, to change the CGM as well. In fact, we've been arguing that you shouldn't just think about CGM as collateral damage in all of this. I mean, one of the reasons Miller's work is so exciting is that I think to us, the CGM is doing the quenching. So what happens in these three cases, which, as I say, there's no difference between them except small differences in when the collapse history, when it collapses. You end up with a completely different fraction of the cosmic baryon fraction in your CGM. So in the case where you don't really have any major mergers, you basically retain all the baryons in the CGM. In the case where you have a sort of moderate merger, you get rid of some of the baryons. And in the case where you have a giant big merger, you get rid of basically all the baryons in the CGM. And our claim is that is the quenching. Because if you get rid of the baryons in the CGM, they are not coming back because the densities are low, the cooling goes like density squared, and there is just basically no way to refuel that galaxy in a sensible amount of time, especially if you have just a little bit of ongoing AGN feedback just to stop cooling instability setting in. Then that CGM quenching has done for the galaxy. It doesn't matter what's in the ISM. All the stuff that people talk about star formation rate criteria within galaxies is irrelevant at this point. If there is not a supply in the CGM, if the CGM cannot cool, you cannot fuel a galaxy. All it can do is exhaust whatever star-forming gas it's got left, and then it's done. So that's our argument at the moment based on these simulations. I should say, you don't just need, it's not just like one merger that can do this. And Nicole has this beautiful paper where she untangled a super complicated scenario where all sorts of things are going on. So it doesn't have to be some big head-on merger. It can be a complicated effect to do with the story of exactly how different mergers interact. But something that disrupts the galaxy a little bit, lets the AGN do damage, especially to the CGM, and then that is the thing that then makes it really hard to cool more gas, enough more gas to reignite star formation. So where are we going with this? Well, we really want to explain the Hubble sequence. So no big deal. That's the goal of the project. Right now, we've just finished running some 10 parsec resolution Milky Ways with Binta physics. So this, again, apologies, this is the Ramses code. I'm really hoping we get back to using Changa soon. But I mean, you all know the reasons we're not right at this moment. Some of them have been spoken about already. So we have this series of Milky Ways with just slight differences in especially their most recent major merger. And there's a ton of interesting science to come out of this. I can't say too much at the moment because there's a bunch of students and so on working on this. I don't want to steal their thunder for when the results do come out, but watch this space for the differences between these galaxies. We're hoping to get some papers out a bit later this year. In the meanwhile, just on arXiv this week, Corentin Cadieux has published a really nice test within this kind of framework of what happens if you, instead of changing a merger ratio, you change the angular momentum of the collapsing gas. And to cut a long story short, it pretty much does what you expect in that if you reduce the angular momentum in the early universe of the region that is providing the gas to your galaxy, then you end up with things that are relatively compact. So here he's got an effective radius of about 1 kiloparsec. This is at redshift 2, by the way. He's doing this experiment at redshift 2 because that's a kind of interesting time where the Hubble sequence is just getting established. So if you have a kind of low angular momentum gas accretion, you get something that's got an effective radius of about 1 kiloparsec, bulge ratio of about 0.72. Whereas as you dial this up, the thing gets more extended. Unfortunately, it's not coming out brilliantly on this screen. But the effective radius kind of goes up to here. It's about 1.3 kiloparsecs, and the bulge ratio is coming down. And it's very interesting to see how that happens. It's all to do with the way that the alignment of infalling structure changes, not just the alignment, but the timing of the infall. So this is showing you the stellar angular momentum as a function of time in this galaxy, and you'll notice there are jumps. The blue, the kind of the colors, these are all basically the same galaxy, but they've had their angular momentum changed in the initial conditions. And so blue is the least angular momentum, red is the most angular momentum. You'll see at the end, the red one, indeed, the galaxy does have more angular momentum, so it works. If you change the early angular momentum, it does work to change the angular momentum in the galaxy at late times. And the blue one has less angular momentum. It also changes the timing of infalls of significant mergers. So if you have high angular momentum, it just takes a bit longer for you to spiral in and reach the central. So this opens up not just studying the direct effect of angular momentum on the central disk, but I think also to think about experiments where you change the merger time and the merger angle into a galaxy and see what effect that has as well. So I am 1/3 of the way through the talk with 5 minutes to go. It's not, I'm not clearly not going to get through everything. I knew I wouldn't. But let me say a little something about stellar masses in dwarf galaxies. So we also have this edge set of simulations. So these are really very, very high. These are like 2 parsec resolution simulations of ultra faint dwarfs. You really need to get to that kind of resolution to, I would claim, to resolve what's going on in the ultra faint dwarfs, because it changes everything. And that is not at all to detract from the amazing work being done in other parts of the collaboration. I think that's definitely pointing the way. But I think we should expect that as we go to higher resolution, all the way down to a couple of parsecs, things will change, unfortunately. The other thing that we find in this suite is radiative transfer. Switching it on and off just changes everything as well. So it's a slightly painful situation with ultra-faint dwarfs. I think we still have a long way to go to understand them. In any case, we're doing our best. These things form in the field. So one thing that we're very obviously missing that, say, other parts of this collaboration are not missing is we're missing environmental effects on these things. But we're just interested in what happens to these very low mass objects in the field. And what we find is, I paused it here at the moment, that there's some gas that's actually forming stars in loads of very, very low mass objects. So this is about redshift 8. Reionization is about to sweep through this box. So when reionization sweeps through, it evaporates all the gas pretty much from all the small things, and everything dies off. That's a well-known effect. It's very hard to form stars after reionization in low mass objects. But that poses the question, how does the assembly history around reionization interact with the timing of reionization itself? So we can make changes to the initial conditions. We can have these things collapse earlier or later. And then, okay, you're used to this now. It's 2 versions of the same universe. They basically look very similar, but you'll find right around the time of reionization, the thing on the left has formed a much bigger galaxy than the thing on the right. In the end, they're going to reach exactly the same halo mass. So in terms of the dynamical mass, it's exactly the same at redshift 0. It's just hugely different at reionization. And what you find is that the stellar masses differ by an order of magnitude. So because of this way that a small timing shift at reionization can change when star formation is cut off in these things, the stellar mass can change by an order of magnitude. And it's not just the stellar mass. When you look at this case, which really struggled to form anything before reionization, actually a lot of its mass takes place, a lot of its stellar mass comes from mergers. So these are tiny little things that all formed a tiny bit of stellar mass that then merge in and increase the stellar mass at late times. It also happens in these 3 galaxies, by the way. It's just that you don't notice it in these 3 because this is a logarithmic scale. So the fraction of the mass being contributed by the mergers is almost irrelevant for the top 3 cases that managed to form a good number of their own stars. So if you plot this on a diagram of V-band magnitude versus half-light radius, this is relevant for how easy a dwarf is to discover, right? Because down here, even if it's actually reasonably bright, it's really hard to find because it's just so diffuse. And you find it really kind of comes across. So you know, it looked on a previous slide like the main effect is the reducing stellar mass. But now actually here it looks like the main effect is the increasing size of these things, which makes these things very hard to detect, in fact. So I have a question mark, like how many things should we expect to find right down here, 31, 32 magnitudes per square arc second? Very sensitive to the physics, it's very sensitive to the history. On top of that, you've got to put on all the physics that's going to come in when this thing falls into the local group and the Milky Way. So I think we have a huge amount to understand. And I think when we look at M star, M halo at the faint end, I almost feel like it's premature to say that we can even start to tie that down, because I'm really scared about the kind of uncertainties that we're seeing there. So I am out of time. So I will skip over the machine learning stuff. I'll say all our software is available. Please use it. Please bug us if there are bugs. And then I will just put up my conclusions. Thanks very much.
All right, lots of questions. Okay, I didn't see who was first, so we'll start with Xijing. I think, or did you?
Andrew, very exciting work. This is Urmila Chedai-Murray. These controlled experiments tell us, if there's a change X in the initial conditions, as a small change, then it's going to have this significant effect at later times, and that's really helpful. So, for example, things like, the major effect on the CGM, right? Very insightful. However, at the end of the day, what we're observing is going to be a statistical distribution, right? So you might have varied the assembly history of a single object, but if you have a large volume and you have a lot of galaxies, really what's happening is that they have a wide variety of, of accretion histories. So do you really, can we really solve the problem about the discrepancies between the observed and the simulated CGMs, for example, by resorting to this argument? Because this seems like just changing one iteration, whereas in reality, galaxies will have a wide variety of assembly histories.
Yeah, so it's a great question and a very complicated question that we can probably talk about for half an hour. I think, let me try and give you a short answer. The short answer, this does not replace the need for statistical samples, that's for sure. It's in the end, as you say, the real universe has a statistical sample. We have to be able to match against that. So what we're really trying to do is understand the why of galaxy formation. And I would argue that is just as important as understanding the what, which is given to you by statistical samples. On top of that, sometimes we can try to get a bit ahead of the curve because we're very efficient in probing the effect of important changes. We can go to higher resolution than you can at any given moment with a statistical sample, where you just need a large number of objects to start pulling out the kind of things that we're talking about. So I think there's an efficiency in it. There is an argument for we have to understand why things are happening, especially given all the uncertainties, because if we don't understand why simulations do something, I would argue we should not really be taking them as the ground truth for comparison to observations. So we need to understand why. We can be ahead of the curve, but yeah, it's not a replacement for statistical samples in the end.
Hi, this is Xijing Shen. It's very exciting. I'm just curious, and how do you change angular momentum in your initial condition? Is it in the code, in the GenEd IC code already, or?
Yep. Everything is public.
This is really cool.
From day one, we make everything public, so you can go and take a look. It's detailed in Corentin's previous paper, but I mean, in brief, we're using tidal torque theory. So tidal torque theory links angular momentum in the early universe to angular momentum in the late universe. So we can use that as a kind of way to say, what should we expect to have to change in the early universe to get this to work? And indeed, it does work. A bit like we use Pressure theory or extended pressure theory to kind of motivate, well, what changes do we have to make different merger histories?
Okay. I'm not sure if I fully understand, but we can talk about it.
Maybe we can talk some more, yeah.
Thank you.
Hey, Andrew. Going back to the variance in that that you showed, it seems like the variance was much greater in the early merger simulation than in the simulation. Do you want to comment on that?
Absolutely. I mean, I think this is implicit, in fact, in Ben's work already, but it's very noticeable here. So I think you're talking about like here in the CGM, for example, and on the previous in star formation rate. Yeah. So what's going on there is that the AGN feedback is just super sensitive to small changes. Just like one particle going past the black hole particle in a slightly different trajectory can make the difference between it fires now or it doesn't fire now. And then there's a kind of amplification effect that I think Ben talked about in his paper, which amplifies these things. So so when the AGN is really important to deciding what happens, then you really start to see the stochasticity. But what's good is that you can still see the overall trends, right? The trends are very clear above that level of stochasticity nonetheless.
Okay, one more.
Hi, Michael Tremmel asking. I actually have a follow-up question to Tom's. I was going to ask something different, but I mean, in this case, such low star formation rates, are you also affected by limited resolution? Because when you're calculating star formation rate, it's, you know, either a star forms or it doesn't, and so there's kind of an inherent stochasticity in that as well. Are you being affected by that here, or is your mass resolution good enough that you can really tell the difference for long periods of time between forming one star every billion years or like a star that, you know, happened to form 25 million years ago? That makes sense.
Yeah, I see what you're saying. So yeah, I think it's like a shot noise effect in the star formation rate estimates. I think you're right that if you go to the far right-hand end, you'll probably, a lot of that is coming from exactly that effect. But if you look here while the transformation is taking place, where the specific star formation rates are actually quite a bit higher, I don't think that's the dominant effect.
All right, if there are no further questions, let's thank Andrew again.
Good morning, everyone. I'm speaking from Tenerife in the Canary Island, where I work at the Instituto de Astrofísica and University of La Laguna. And so today I've decided to talk generally about a lot of topics that we're covering as a group, not just about my staff, but also all of our students and postdocs. So these are my collaborators at the moment: Chris Brook, Mark Huerta's company, Robert Grant, and Giuseppina Battaglia. They are all based here in Tenerife. And then long-term collaborators, Andrea Maccione, Libeskin, and Oliver Newton. I currently have a postdoc working with me, Andrea Negri, and together with other people, we are supervising 2 PhD students and 3 master students. Before getting into the science that we're doing, I'd like to give you a very brief overview of all the simulation we're using. So you're all expert in this field. I don't have to go too much in detail. We're using local group simulations and zoom-in simulation. For the local group ones, we are using CLUES, STIA, and NIHAO local group. The CLUES simulation are constrained initial condition. Local group simulation run with the code gadget are quite old simulation now. They are, of course, hydrodynamic. They were run about 10 years ago. The STIA simulation are much newer. They run with the code repo. And finally, NIHAO local group are simply CLUES simulation rerun with the NIHAO feedback. And I think the paper just came out this year. And for the zoom-in simulation, we use in Magic, NIHAO, and Auriga. So you can see there is a variety of codes that we're using for our studies. As I say, I like to cover just with 1 or 2 slides a lot of topics that we are currently working on. For what regards the Milky Way, we are working on constraining metal diffusion models by looking at low metallicity stars and gas metallicity within the solar neighbors. And then I will move to the regime of dwarf galaxies, where we are much more active. And I'm going to look at in detail at ultra-diffuse galaxies, in particular at their metallicity gradients and density profiles. Then I will dig a bit into the star formation histories in local group dwarfs. I will then talk about the impact of AGN feedback on dwarf galaxies. And finally, I will end with machine learning methods applied to the cusp and core determination. I was a bit sad that Andrew didn't talk about what they're doing on machine learning. I was hoping to get some details. So let me start from the Milky Way. There is a recent Nature paper by Desia and collaborator just last year, in which they calculated line of sight neutral gas metallicities around the solar neighborhood. And surprisingly, they found that the scattering this metallicity is much larger than previously expected. So our idea is, if we can trust these observations, can we use this observation to constrain metal diffusion models? So we're doing this work together with Jorge Sarrato, he's a master's student. And what I'm showing you here in these two images is a Milky Way, simulated Milky Way within the Nihao local group simulations run with and without metal diffusions. It's particularly interesting because it's exactly the same initial condition and exactly the same galaxy, just done with and without diffusion. You're seeing here a map of the gas color-coded by its metallicity in the solar neighborhood, where you can see immediately that the case with diffusion here on the left, the gas metallicity is much more homogeneous than the case without diffusion. So it turns out that in order to reproduce the Desia et al. Scatter, we need something in between. So we need to turn a little bit, possibly our diffusion coefficient, to get similar results to the observed one. Another way to look at this, or another manner to try to constrain diffusion, is by looking at low metallicity stars in the solar neighborhood. So Sestito and collaborators found metal poor stars in the Milky Way disk. And so the question is, what is the origin? And also, can we get some extra constraint on diffusion looking at the stars? Once again, I'm showing you here the same Milky Way galaxy from Nihao run with and without diffusion. And here I'm showing you the metallicity versus age plane. And you can see the incredibly small scatter that we have in the case of having metal diffusion. Actually, over here, 11 gigayears ago, you can see a merger. This is compatible with the Gaia and Cyrus merger. And in the case of not having metal diffusion, you can see that you produce many, many more low metallicity stars. By low metallicity, I mean less than minus 2.5. So perhaps this can be an extra constraint to try to tune our diffusion coefficient, just to look at observation of disk stars with low metallicity and different ages. So this is a paper in progress. Moving now on the dwarf galaxy regime, we've been done a lot of work on ultra diffuse galaxies. As you know, ultra diffuse galaxies have the stellar mass of a dwarf, but the size of a large spiral galaxy. So they're extremely faint and diffuse and difficult to find. This is a paper that we just put out on arXiv last week with our PhD student, Salvador Cardona, in which in detail, we look at the metallicity profiles of stars, stellar metallicity profiles in Nihao simulation UDGs. In this image, you can see such a metallicity profile. Nihao simulations are shown in blue, and they're compared with local group dwarf galaxies as dashed line from a very recent paper by Taibbi and collaborators, also just came out last week. So you can see that the expected stellar metallicity profile is very similar between local group dwarfs and ultra diffuse galaxies in simulation. So in this sense, UDGs are not peculiar. What we do not match is the only so far reported case of an ultra diffuse galaxy with a positive to flat metallicity gradient. This is Dragonfly 44, shown here as black points. The relevant paper is Guillaume and collaborator. So we are predicting here that this Dragonfly 44 is an outlier, actually. We are predicting that when more data, hopefully soon, will be available of observed UDGs, their metallicity should be flat to negative. We then investigated how this metallicity gradient actually arises. So they are set by the interplay between the radius at which star formation firstly occur and the subsequent supernova feedback, which is able to redistribute stars within the galaxy. This is, as you know, the model put out by Fabio Bernato and Andrew Ponsen a few years ago, in which supernova feedback launches strong outflows, and this can evacuate from the center of the galaxy both dark matter particles and stars. And so what happened is that this affects the final metallicity distribution in these galaxies. I'm dividing here in these two plots, I'm dividing the UDG population into rotation supported on the top and dispersion supported galaxies on the bottom. And I'm showing the initial original metallicity profile in red, just by using the birth radius of stars, and the Redshift zero metallicity profile in blue. So you can see, for example, in the rotation supported case, in which star formation proceeds inside out, we originate a positive metallicity gradient, which gets subsequently flattened by stellar feedback that moves all stars from the center of the galaxy to the outskirts. And in the case of dispersion supported galaxy, this supernova feedback actually acts by steepening even more the profile. Another aspect of UDG that we are interested in, and we put out a paper last year with Chris and Andrea, is to look at the density profiles of observed UDGs. The question we want to answer is, are UDGs similar to low surface brightness galaxies? In the sense, do they show cores? You know that the strongest signature of core happens exactly in low surface brightness galaxies. So we took one of the few, possibly one of the only so far reported rotation curve of a UDG, AGC 24-2019, and we fit this galaxy with an NFW and with a chord model. And so you can see directly here that for what regards the fit, both models gives a reasonable fit. But the thing is that when we fit with an NFW, the returning concentration parameter is extremely small, is about 2, which is 5 sigma of the concentration mass relation. I'm showing here the concentration mass relation. When instead we use an expanded Elo model, the concentration parameter comes very much in line with expectation. And also the galaxy in this case would have an inner slope of 0.5, which is in line with the expected. This is inner slope versus stellar mass coming from different simulations. So this is in line with what we expect from simulation that form a core. So in this sense, UDG at the moment seem to be in line with the general population of low surface brightness galaxies. We then move, well, we were interested as well in the star formation history of the general normal population of local group dwarf galaxies. And what we did in a paper last year with Alexander Neve and Julio Navarro is we found, using Clue simulation, we found a correlation between star formation bursts in satellite galaxies and their orbit. In particular, we found a burst of star formation, which you can see here on the right side of this plot, just when the satellite approaches pericenter of its main galaxy. So one condition for these satellites to actually retain their core gas, which gets compressed at pericenter, is that the orbit is not too eccentric. So pericentric approach larger than 10 kiloparsec. And interestingly, we found that this also affects the star formation history of the host galaxy itself. I'm showing here the star formation for Andromeda galaxy on the left and the Milky Way. And you can see that when satellites infall and reach the pericenter of these host galaxies, especially when satellite infall as a group, which you can see down here, about 8 gigayears, there is a visible peak of star formation, which is a visible signature in the host star formation. So these findings are kind of in line and in agreement with what has been reported recently in observation. We saw the impact of Sagittarius dwarf galaxy on the Milky Way star formation history. I only have 2 slides to go. I realize it's a lot of things. We've been looking at the impact with PhD student Elena Arjona. We've been recently looking at the impact of AGN feedback in dwarf galaxies. And in particular, we've been using the Auriga simulations. So there is observational evidence that show that AGN feedback is very important also in regulating the evolution of dwarfs. See, for example, the paper of Mesqua, 2018. So what we did is we ran 12 dwarf galaxies from Auriga with and without AGN. These are quite massive dwarfs. Stellar mass is 10 to the 9 to 10 to the 10. And what we found is that the stellar mass with AGN is smaller than the stellar mass of the galaxy run without AGN. You can see this here in the M-star and Melo plot. AGN galaxies are shown as points and no AGN are shown as crosses. So AGN seem to be a viable mechanism to, quench or suppress star formation. However, we found that this effect it's only happening when the halo mass of the when the mass of the black hole is large enough. So we found it for black holes, mass is larger than about 10.6.4. And finally, in the very last minute of my talk, I'm gonna, I guess, disclose some of the machine learning stuff we're doing with master student Julian Exposito. The question we want to answer is, I don't know what to call this thing. The question we want to answer is, can we infer the central slope, the central dark matter slope of a dwarf galaxy just by having spectroscopic information about line of sight velocities and positions of its stars? As you know, Gaia provides very good data about these two quantities. And so what we did is we trained a neural network with about 250 simulated dwarf galaxies, and we are increasing our sample every day. Halo masses between 10 to the 9 and 10 to the 11.5, and we train this neural network. The output of this is a probability distribution function shown here that a certain galaxy has a certain slope. But of course, here I'm showing you a very good example in which the recovered value is pretty close to the true value of the dark matter central slope. And on the bottom plot, I'm showing real minus predicted value as a function of central slope. You see that an important thing in order for the neural network to work is that we need to have an unbiased sample covering all possible slopes. And you can see that pretty much the neural network works fine at every central slope. In red, these errors come from just looking at each galaxy at different viewing angles. So I guess that's enough. This is what we're doing as a group. I leave you here with my conclusions. And if you're interested in any of this topic or you want to collaborate on any of this topic, please send me an email over here. And thanks for your attention. I can't hear anything.
We have some questions coming. Farah?
Okay. Reina, thank you for a great talk. This is Farah. I was wondering, with your black hole and dwarf galaxy results, right, with black holes that massive, do they lie on the kind of M sigma relationship that we'd expect, or is that overmassive compared to that?
So the galaxies themselves are a little bit overcooled, I would say, in this Auriga simulation. They have too many stars for their halo mass, and also their black holes are quite massive. But I think is that what we're trying to do at the moment is a comparison of the same galaxy with and without black holes. So we're not caring too much if the galaxy does not lie perfectly on the M-star M-halo relation. But within those galaxies, the black holes, yes, they follow the expected black hole sigma relation.
Thank you.
Hi, Ariane. It's Tom Quinn. So Rock Roshkar and Victor Di Battista explained the breadth of the solar neighborhood metallicity distribution function in stars from radial migration. And I'm wondering, sort of the spread in metallicities in the gas, could that be the same mechanism, or is it, you think it's different?
So, I mean, I think, well, first of all, this Nature paper is about, there is a bit of a controversy, I would say, on this, the SIA paper, because just last month or something like that, or 2 months ago, there was another paper that came out saying that perhaps the scatter that they found in gas metallicity in the solar neighbor is not as extreme. So we think that the SIA is very extreme scatter. There are other studies that didn't find any scatter at all. So I don't know. I don't even know at this stage if there is such a scatter, there is such a spread. We were doing this work, we were almost finishing this work when another observational paper came out saying that the SIA results are too extreme. So we are a little bit on, I don't know the answer to that. Possibly it could be, but possibly the scatter doesn't even exist in such a big amount. So I guess we have to wait a little bit more for more observation to confirm it or not.
Yep, go ahead.
Hi, it's Michael Tremmel. I'm going to bring it back to the black holes a little bit. So I mean, first of all, that's awesome stuff. I think it's really cool. The fact that you need very massive black holes to begin to have an effect on the galaxy, how much do you think that could be affected by, as you say, the overcooling that's already taking place? Is it possible that the same overcooling is taking place with AGN feedback to make it artificially less effective in those simulations?
Say it again. Is it possible that?
So you mentioned that the galaxies that you've tested are overcooled and that they have too many stars. So presumably the supernova feedback is not as effective as it should be. Do you think that the AGN feedback might be having the same issue where the feedback is maybe artificially less effective because of numerical effects?
Right, I don't know. We can look into it, but for the Auriga dwarf galaxies, they don't have any supernova feedback in the same way that we do with offline simulation. Like they don't have any supernova feedback creating cores or ejecting dark matter and stars a la blast wave Stinson. So well, we have to look more into that. We just started the project.
Okay, thanks.
All right, let's thank Ariana one more time.
Thank you.